Welcome to the deep dive. You know how AI is now crafting some pretty wild images and even speaking surprisingly naturally?
Yeah, it's moving fast.
Well, the world of AI music generation is hitting a new level, especially with the rise of something called diffusion models. And for you who wants to stay sharp on these advancements without getting, lost in the weeds, we're taking a look at a fascinating new paper, Mustango, toward controllable text-to-music generation.
Exactly. And what's really exciting about Mustango, I think, is its focus on giving creators like you much finer control over the music that's generated from text.
Finer control.
Yeah, instead of just a general musical style, we're talking about the ability to specify things like the chords, the rhythm, the speed, even the key the music is in. It's about moving beyond like a broad brushstroke to having real precision.
Okay. And a key challenge in getting to this level of control has been the data, right? You need music paired with really detailed text descriptions that include specific musical information.
Precisely. The team behind Mustango recognized this, and as part of their work, released a brand new data set called Music Bench.
Music big.
It's massive, over 52,000 examples, and crucially, these examples have text descriptions that incorporate actual music theory elements like chord progressions and tempo markings. Think of it as a much richer training ground for the AI.
Right, so the data set itself sounds like a big deal.
The creation of Music Bench is definitely a significant step forward in itself, providing the kind of detailed data that can really fuel progress. But the heart of Mustango is its core innovation, a component they've named UNE, short for Music Domain Knowledge Informed UNet.
You mean it?
Imagine it as a specialized guide within the AI that focuses specifically on the musical aspects of the generation process. It doesn't just look at the overall text description. It also hones in on specific musical instructions, things like the chords, the beat, the tempo, the key that are extracted from that more detailed text. This allows for much more targeted music creation.
Okay, let's try to break down the high-level picture of how Mustango actually works for you, the listener. At its core, it uses what's called a latent diffusion model.
Uh-huh.
You might have encountered similar models in image or audio generation. The fundamental idea is that the model learns what music sounds like by taking existing music and gradually adding noise until it's, well, unrecognizable,
Right.
and then learning to reverse that process starting from noise and step by step reconstructing musical sounds.
And what's particularly clever about Mustango is how it manages that reconstruction process. That's where Munet comes in. Think of Munet as the brain that steers this denoising and rebuilding of the music.
The brain. Okay.
It's not just interpreting the general sentiment of the text like a calm piano piece.
Okay.
It's also actively looking for and using specific musical cues within the text, such as in the key of D minor or with a moderate tempo.
Ah, so it uses both.
Exactly. Munet uses both the broad textual understanding and these very specific musical directions to shape the final piece of music it generates.
Yeah.
So, in essence, Mustango listens to your text description on two levels: the general idea and the specific musical instructions.
But that gives us a good overview. So let's now dig into how they built this capability, maybe starting with this really interesting music bench data set you mentioned.
Absolutely. The level of control that Mustango offers really comes down to the richness of the data it was trained on, and that's where Music Bench shines. It's built on an earlier data set called Music Caps,
Right, I've heard of that one.
which had around 5,500 music clips with descriptions. The Mustango team expanded this dramatically, creating a data set about 11 times larger. They did this through two main approaches: making the descriptions more musically detailed and making the underlying music more diverse.
Okay, let's start with the descriptions. How did they make them more musically detailed?
Well, they used some really sophisticated tools from a field called Music Information Retrieval, or MIR for short.
MIR, okay, music information retrieval.
Yeah. Think of MIR as the science of computers listening to music and automatically pulling out meaningful information. They use these tools to analyze the audio in the original Music Apps dataset and extract things like the precise timings of beats and downbeats, the rhythmic backbone, the underlying chord progressions, the key the music is in, and the tempo measured in beats per minute. They use specific software like BeatNet for rhythm analysis, Chordino to identify chords, and Essentia's key extractor to determine the key.
Wow, okay, so they're essentially teaching a computer to hear music the way a musician does, at least in terms of these fundamental elements. Can you give us an example of the kind of details they were able to extract?
Sure. For tempo, they might get a reading of, say, 120 BPM, indicating a fairly fast pace.
Okay.
For chords, they could identify a sequence like C major, G major, A minor, F major, a very common progression. For the key, they might determine G major. And for beats, they'd essentially map out the rhythmic structure, like 4 beats per measure, and precisely when each beat occurs.
Okay, so they have all this detailed musical information extracted from the audio. How did they then link it back to the text descriptions to create this richer data set? That seems key.
This is where the clever part comes in. They created templates, essentially pre-structured sentences, to convert these raw musical features into natural language.
Templates, right.
So, for example, a tempo of 120 BPM might be turned into a sentence like, the tempo of this piece is 120 beats per minute. Or perhaps something more descriptive like, this song has a lively tempo. A chord progression like Am C minor 7 G could become, the song features a chord progression of A minor, C major 7th, and G major.
I see.
These newly created sentences, which they called control sentences, were then added to the original text descriptions from music apps, providing much more specific musical context. You can actually see examples of these sentence structures in their paper's appendix.
That makes perfect sense. So the AI now has text that doesn't just describe the mood or instrumentation, but also gives it concrete musical parameters. What about the second part you mentioned, making the music itself more diverse?
Right? Diversifying the audio. To increase the variety of the music in their training data, they applied several audio transformations. Firstly, they adjusted the tempo of the original music, making it slightly faster or slower, by anywhere from 5 to 25%.
Okay, a decent range.
Secondly, they altered the pitch, shifting it up or down by a small amount, up to 3 semitones. They kept this range relatively subtle, to avoid making the instrument sound artificial.
Makes sense.
And thirdly, they played with the volume, introducing gradual increases, crescendos, or decreases, decrescendos, over the course of the music.
And I'm guessing they didn't just change the music without updating the corresponding text descriptions. That would mess things up, wouldn't it?
Absolutely not. Good point. The text descriptions were also adapted to reflect these changes in the audio. For instance, if the tempo was increased, the description might be modified to include words like faster or more upbeat.
Got it.
They also employed another smart strategy to make the model more resilient. For some of the augmented examples, they randomly removed a few of those control sentences we just discussed.
Oh, interesting. Why do that?
Well, it forces the model to learn to generate music even when not all the specific musical details are explicitly given in the text. Makes it more robust. They even used a large language model, ChatGPT actually, to rephrase the original text prompts in different ways, adding even more linguistic diversity.
Clever.
And finally, they filtered out any samples that mentioned things like quality or low fidelity to ensure they were training on a high standard data set. All of this resulted in the very large and detailed Music Bench data set.
Okay, so we have this incredibly rich data set, Music Bench. Now let's get into how Mustango actually uses this information to generate music with this enhanced level of control. What's the underlying architecture look like?
Right. Mustango's system has 2 main parts working together, as we touched on earlier. A latent diffusion model, or LDM, and their key innovation, the MUNET module.
LDM and MUNET.
They opted for an LDM approach, similar to other recent models in the field like Tango and Audio LDM, because it helps to make the whole process much more computationally efficient.
Yeah.
Instead of directly manipulating the raw audio waveforms, which are very data-heavy,
Yeah, huge files.
the LDM works in the more compressed, abstract, latent space.
A latent space, that sounds a bit technical again. Can you explain what that means in simpler terms, especially in the context of music?
Sure. Think of it like this. Imagine you take a complex musical piece and distill it down to its most essential characteristics, the melody, the rhythm, the harmony, into a more compact representation.
Like a summary.
Kinda, yeah. This compressed form still captures the core essence of the music, but is much smaller and easier for the AI to work with. Mustango uses a special type of neural network called a variational autoencoder, or VAE.
VAE. Okay.
Which was actually pre-trained on a large amount of audio data from the Audio LDM project to perform this compression. It essentially encodes the audio into this lower dimensional latent space.
Got it. So they're operating on a more streamlined version of the music. Now, how does the diffusion process itself play out in this latent space? You mentioned adding noise and reversing it.
Exactly. It follows the standard steps of a diffusion model.
Right.
First, there's a forward process where they gradually add random noise to this latent representation of the music until it becomes completely random. Just noise, losing all musical structure.
Okay.
Then the crucial part is the reverse process. This is where the model learns to take that noisy latent data and, step by step, remove the noise and reconstruct the original clean latent representation of the music.
And Munet is the component that guides this reverse process, effectively telling the model how to denoise the latent data in a musically meaningful way, right?
Right.
Using those instructions.
Precisely. Munet is really the engine of Mustango's controllability. It's a type of neural network called a UNet, which is common in generation tasks, but with important additions called cross-attention blocks.
Cross-attention.
Yeah. Its main job is to take the noisy latent audio at each stage of the reverse diffusion and denoise it based on the specific instructions we give it. In Mustango's case, these instructions come in three forms: the general text description, the beat information, and the chord information. So we now looks at all of these inputs to figure out how to best remove the noise and reconstruct music that aligns with all of them.
You mentioned earlier that Munet has two specific encoders within it, one for beats and one for chords. How do those work to get the musical information into a usable form for the main network?
Right. Good question. So InnerBeat, the beat encoder, takes the extracted beat information, both the type of beat within a measure, like the first, second, third, or fourth beat, and the precise timing of each beat in seconds, and converts it into a format that Munet can understand. For the beat type, they use a common technique called one-hot encoding, which essentially creates a unique digital label for each type of beat. For the timing of the beats, they use something called music positional embedding, or MPE. Think of MPE as a way for the model to understand the temporal relationships between different musical events, in this case, the beats. These two pieces of encoded information are then combined and processed by a neural network layer to create the final beat features that UNet uses. And as we discussed, they use BeatNet to initially extract this raw beat information from the audio.
Okay, that makes sense for beats. And how does the chord encoder incorrect handle the more complex information about chords? Chords have more parts, right?
They do. It's a bit more intricate because chords themselves have several characteristics. It goes four key aspects of a chord: the root note, like C, G, or A, the type of chord, major, minor, dominant, seventh, etc., whether the chord is inverted.
Inverted.
Yeah, meaning a note other than the root is the lowest note. And finally, the precise moment in time when the chord occurs.
Okay. Four aspects.
For the root note, they use a technique called fundamental music embedding, or FME. This is a really insightful approach because it understands the inherent musical relationships between different pitches, for instance, recognizing that C sharp and D flat are essentially the same note in many musical contexts. They are enharmonically equivalent.
Oh, that's clever. It knows some music theory.
Exactly. For the chord type and inversion, they again use one-hot encoding to create distinct digital representations. And similar to the beat encoder, they use music positional embedding, MPE, to encode the timing of the chords. All of these encoded components are then combined and processed by another neural network layer to produce the chord embeddings that Munet utilizes. And they rely on Chordino for the initial extraction of the chord information from the audio.
So Munet receives these encoded representations of the text, the beats, and the chords. How does it actually use them during that reverse diffusion process, the denoising, to generate the music? You mentioned cross-attention.
Exactly. This integration happens through the cross-attention blocks within Munet. Attention mechanisms are a way for a neural network to focus on the most relevant parts of its input when making a decision.
Okay.
In this case, the main UNet part of Munet is processing the noisy latent audio. The cross-attention blocks allow it to selectively attend to the text embedding, which comes from a language model called Felan T5, the beat embeddings and the chord embeddings.
So it looks at all three condition types.
Right. And what's interesting is the order in which they apply this attention. The researchers found it beneficial to prioritize applying cross-attention to the beat information first and then to the chord information.
Oh, why that order?
Their reasoning is that a consistent and well-defined rhythm is a foundational element of most music. So establishing that first helps to provide a strong framework for the harmony to then be built upon. It's like ensuring the rhythmic foundation is solid before adding the melodic and harmonic layers on top.
That makes a lot of intuitive musical sense, actually. But what happens if the user's text prompt doesn't explicitly mention things like beats or chords? Can Mustango still generate music that has, a sense of rhythm and harmony? Or does it fall apart?
No, it doesn't fall apart. It can still handle that. During the inference phase, that's when the model is actually generating new music based on a text prompt. If the prompt doesn't include explicit beat and chord information, Mustango uses two separate AI models that have been trained independently to predict these musical features directly from the text.
So it has dedicated AI models that act as guessers for the rhythm and harmony based on the text alone.
Exactly. like little helper models. For predicting the beat, they use a large language model called DeBerta-Large. This model takes the text caption as input and predicts two crucial things: the overall beat count or meter of the music, whether it's in a time signature like 44 or 34, and the sequence of time intervals between the beats.
Can you give an example?
Sure. If it predicts a beat count of 4 and intervals of 0.5 seconds, 0.5 seconds, 0.5 seconds, and 0.5 seconds, it understands the music is likely in a common 44-time signature with beats occurring every half second. It continues to predict these beats up to the 10-second limit of the music it generates.
That's a really ingenious way to bridge the gap when the user provides a more general description but still expects musically structured output. It sort of fills in the blanks intelligently. So how well does all of this perform in the real world? Did the researchers conduct experiments to see how effective Mustango is?
They did. They carried out extensive evaluations using both objective, measurable metrics and subjective evaluations where human listeners gave their opinions.
Okay, let's hear about the objective stuff first.
For the objective assessment of the overall music quality, they use metrics like freshet distance, FD, freshet audio distance, FAD, which is designed to correlate well with how humans perceive audio quality, and Kullback-Leibler divergence, KL, on several data sets, including their newly created AMAAI dataset.
And the results?
The results were very encouraging. They showed that Mustango's generated music achieved state-of-the-art quality according to FAD and KL, even surpassing the performance of strong existing models like MusicGen and Audio LDM2.
Wow, state of the art. That's quite an achievement. And what about evaluating how well Mustango actually follows those specific musical instructions in the text? Its controllability. That was the main goal, wasn't it?
Exactly. To assess controllability, they used a modified version of their FMA CAPS dataset as well as their Test B dataset, both of which contained text prompts with explicit musical control sentences, clearly stating the tempo, key, chords, and beats.
Okay.
They then generated music based on these prompts and automatically extracted the musical features from the generated audio using the same MIR tools they used for creating Music Bench. They defined 9 different metrics to measure how accurately the generated music matched the instructions in the text.
9 metrics? Like what?
Yeah. These metrics included things like whether the generated tempo fell within an acceptable range of the target tempo, if the generated key was correct, and how well the sequence of generated chords aligned with the specified chord progression. For chords, they looked at both exact matches and also considered musically similar chords, or even if the correct chords were present but maybe in a different order. They also had a beat matching metric.
Right. Pretty comprehensive. And what did these evaluations reveal about Mustango's ability to be controlled through text? Did it work?
The results were quite significant here, too. Mustango demonstrated particularly strong control over the key, and especially the chords of the generated music. It outperformed other models by a considerable margin in accurately producing the specified chord progressions.
So it really nailed the harmony control.
Yes. Interestingly, the level of control over tempo and beats was more comparable across the different models they tested. The researchers suggest this might be because the original MusicCaps dataset already contained some implicit textual information about tempo, like words such as slow or fast, which allow the other models to also learn to control these aspects reasonably well.
Ah, okay.
But the specific attention that MUNE pays to extracted chord information clearly gave it a significant advantage in harmonic control.
So the specific design of MUNE, focusing on and processing chord information so carefully, using things like that fundamental music embedding, really paid off in terms of accurately reflecting the harmonic instructions in the text. What about the subjective evaluations? What did human listeners think about the music generated by Mustango? Did it sound good and controlled?
They conducted both general listening tests with a broad range of participants and more focused expert listening tests, presumably with musicians. In the general tests, listeners rated the overall audio quality, how well the music matched the provided text description, relevance, the general musical quality of the generated piece, the consistency of its rhythm, and the overall harmony.
And for the experts?
In the expert tests, they added specific questions that asked musicians to evaluate how well the generated music matched the chords and tempo specified in the text prompts.
Makes sense. And the verdict?
The feedback was largely positive for Mustango. Both the versions of Mustango trained from scratch and those that use some initial pre-training on general audio data perform better than their baseline models based on Tango. and were competitive with or even superior to MusicGen and Audio LDM2 across various subjective metrics.
That's great. Any specific highlights?
Notably, Mustango consistently received high ratings for how well its generated chords matched the text prompts, which again aligns perfectly with the objective findings about its strong chord controllability. It seems both the metrics and the human ears agreed on that point.
They also mentioned conducting an ablation study, didn't they? What did they learn by selectively removing or modifying parts of their model? Sometimes that tells you what's really important.
Yeah, ablation studies are super useful for that. While they noted it wasn't an exhaustive removal of every single component due to, computational limitations,
These models are huge.
it still provided some valuable insights into the importance of different parts of Mustango. One particularly interesting finding was that pre-training the model on a large data set of general audio, rather than specifically music, didn't seem to provide a significant advantage for the task of music generation in this context.
Oh, really? That's counterintuitive sometimes.
It suggests that having music-specific data, as in Music Bench, and the Muse domain-informed architecture of UNE are perhaps more critical factors for achieving high-quality and controllable music generation than just general audio pre-training. The study also reinforced the importance of the MUNET module itself for achieving that enhanced level of controllability over musical elements like chords.
So MUNET really is the special sauce here.
It seems to be a key differentiator, yes.
Of course, as with any research, there are always limitations. What did the authors identify as the current boundaries of what Mustango can do?
They highlighted a few key limitations. Firstly, the current level of detailed musical control in Mustango is primarily geared towards Western music theory concepts: chords, keys, specific meters.
Right.
These concepts might not directly translate or even exist in the same way in other musical traditions around the world, such as various forms of classical music from India or, say, gamelan music from Indonesia. Adapting it would require different kinds of musical knowledge.
That's a fair point. What else?
Secondly, the model is trained on paired data text descriptions linked to specific pieces of music. This reliance on paired data might limit its effectiveness in scenarios where such detailed paired data is scarce. And finally, a practical limitation. Due to the computational resources required, Mustango is currently limited to generating relatively short music clips, up to 10 seconds in length. Extending this to create longer, more complex musical pieces is definitely an important area for future research and development.
10 seconds is pretty short for a full piece of music, but still, it certainly sounds like Mustango represents a really exciting and significant advancement in the field of generating music from text, particularly in its ability to give creators like you much more precise control over the musical outcomes.
I agree. The combination of the richly detailed Music Bench dataset and the Music Domain-Aware MUNET module appears to be a very powerful approach.
Absolutely. The potential for musicians, producers, sound designers, and really anyone interested in music creation to be able to translate detailed textual ideas into specific musical elements is, well, truly groundbreaking.
It really is.
Yeah.
And the fact that the researchers have made both the Music Bench dataset and the implementation of Mustango publicly available is a fantastic contribution that will undoubtedly fuel further innovation in this rapidly evolving field. People can build on it.
Yeah, open sourcing is huge. It really does open up a whole new range of creative possibilities. And on that note, here's a final thought for you listening. Considering Mustango's ability to understand and follow specific musical instructions provided in text, what kinds of entirely new creative processes and forms of musical expression might become possible in the future? How could this technology potentially impact the way we learn about and interact with music, maybe even music education? It's definitely something fascinating to think about. Thanks for exploring this deep dive with us today.